Okay, I'm going to draw a bean in space, basically. So let me first get my coordinate system here. I do think I do like red being my axes. So let's get my y-axis. My x-axis. And my z-axis. And so here's x hat, y hat, and our friend z hat. And so we're going to have some object in space. I want it to have kind of a circular feel, so I'm going to give it kind of an ellipsoidal top, some depth, and an ellipsoidal bottom. And this top surface is going to be defined by some function, z equals some, and we'll call this function 2 in r and theta. And this bottom surface is going to be defined by some function z equals function 1 of r and theta. And then we're going to look at the region that this generates a shadow for in the xy plane. So if we fall straight down from this, this has some shadowed region, R. Get my R being a little more R-like. And so there's the shadow region. And so if we want to figure out our terms of integration, we're going to pick some point M, or some point, in the xy plane, and we're going to pierce through our region. And we're going to call this ray M. And what we need to note is the point where it enters and the point where it leaves our region in space D. All right, so this is region in space D, I guess. And where it enters sets our boundaries for our Z. And so this integral comes in, and z is going to equal this first function in r and theta, and z is going to leave with this second function in r and theta. And so that sets up my dz boundary. And so now we're happy with how we're setting up z. We've taken care of one of our dimensions. And so the next thing we're going to do is we're going to take some ray from the origin and have it pass through this point also. Let's see here. And so we'll call this ray L. And it's going to hit the region now on the xy plane at some r equals a function of theta. And it's going to leave at some r equals another function of theta. So that sets up our second integral here. R r equals h1 of theta, and r equals h2 of theta. And that's going to give us our r dr. Now I'm going to move the r out forward, r dr. And so that sets up our next part of integration. Then the last thing we need to do is we need to set kind of a set of caliper-like or chopstick-like rays that come tangential to our region, that is the projection of our space. And what we're going to note from these is we're going to look at theta 1 to get to the first one, and theta 2 to get to the second one, because that will encompass the whole sweeping that sweeps out the region's area. And so the last part of the integral is from theta 1 to theta 2 d theta. And then, of course, if there's some function that is trapped within this region, some heat function or some density function, that function has to be in terms of r, theta, and z. And so this is the rules that we use for setting up a triple integral in cylindrical coordinates. Let's look at a triple integral in cylindrical coordinates. I think if we want to do this, I will do my examples in another video. This will be the setup, and then we'll bring out examples in the next video.